Hi students, welcome to our YouTube channel NECNTV ET 247. I am Ayasha, Associate Professor, Northern Engineering College, Melbourne. Today I am going to explain reduction of quadratic form to canonical form by orthogonal transformation. I am going to explain this concept by taking one example, that is one problem. So here reduce the quadratic form to canonical form by orthogonal transformation. In this, the first step is we have to write the matrix form of this quadratic form. The matrix form is A is equal to, first we have to write the diagonal elements. These coefficients are diagonal elements. 6, 3, 3. Minus 2yz. This is in which place? That is second row, third column. That is yz place this is. yz and zy. Therefore, here we have to write by 2. Therefore, you will get minus 1 here and minus 1 here. This is this coefficient zx and xz. xz means in the, that is first row and third column. 2 we have to write here, and third row first column zx you have to write 2 here. Like this xy this place, so you have to write minus 2 here and minus 2 here. Like this, we have to write the matrix form of the given quadratic form. That is first step. The second step is you have to find eigenvalues for that matrix. The eigenvalues calculation, first you have to write the characteristic equation of A is determinant of A minus lambda I is equal to 0. So in the next step, we have to write, that is for the diagonal elements, we have to add minus lambda. That is 6 minus lambda, 3 minus lambda, 3 minus lambda. For this, you have to calculate the determinant value. That is, if you write the determinant of this one, you will get the equation. By expanding this, you will get the equation lambda cubed minus 12 lambda square plus 36 lambda minus 32 is equal to 0. If we solve this cubic equation, you will get 3 roots. Lambda is equal to 2, comma 2, 8. These are the repeated roots, 2, comma 2. So therefore, the eigenvalues of A are 2, comma 2, comma 8. After completion of the calculation of these eigenvalues, we have to calculate the eigenvectors. We have to calculate the eigenvectors for these eigenvalues. So eigenvectors, first we have to take case 1. First eigenvalue, lambda is equal to 2. For lambda is equal to 2, the eigenvector formula is A minus lambda I of x is equal to 0. Because our eigenvector formula is A lambda, that is Ax is equal to lambda x. Therefore, here we are writing A in lambda place, we are taking 2 and I of x is equal to 0. For the matrix A, we have to take, that is minus 2 for diagonal elements. In the lambda place, we have 2. So our matrix is, that is 6. First element is 6. 6 minus 2, 4 you will get. The second diagonal element, 2 element is 3. 3 minus 2 you will get 1. So last element, that is 3 element is 3, that is 3 minus 2, 1. So like this we will get the matrix from this, and x1, x2, x3, this is vector is equal to 0. First we have to find the rank of this has become homogeneous equation, system of homogeneous equations. Ax is equal to 0. So in order to solve this system of equations, we have to find the rank of this matrix by reducing into the echelon form. So here I am applying row transformations to reduce this to echelon form. So here first element is fixed and the remaining elements are making zeros by applying R2 tends to 2R2 plus 2R1 and R3 tends to 2R3 minus R1. By applying these row transformations, we get here all zeros rows. So the rank of this matrix is the number of non-zero rows in the echelon form. That is, here the rank of the matrix is 1. So from this we are writing the equations 4x1 minus 2x2 plus 2x3 is equal to 0. See here how many independent variables are there among these three variables means rank is 1. So n minus r, we have here n minus r independent variables. N is number of variables 3 minus rank is n minus r, rank is here number of non-zero rows 1. So n minus 1, 3 minus 1 is equal to 2. So here we have to take two variables as independent variables. So here we have among these I am taking x2, x3 are independent variables. x1 depends on x2 and x3. x2 is equal to k1 and x3 is equal to k2. These two are independent variables and x1 depends on these x2 and x3. Therefore, here we get x1 is equal to 1 by 2. From this equation, we get this one. From this equation, we get this x1. 1 by 2 into k1 minus k2. Therefore, eigenvector is equal to x1, x2, x3. That is 1 by 2 into k1 minus k2, k1, k2. So this can be written as like this, k1 into 1 by 2, 1, 0 plus k2 into minus 1 by 2, 0, 1. Here I am taking k1 is equal to 2 and k2 is equal, we can give any value to this k1 and k2. Therefore, I am taking here k1 is equal to 2 and k2 is equal to 2. So, I will get one vector as 1, 2, 0. The other vector as minus 1, 0, 2. Next, case 2. When lambda is equal to 8. So, our formula to find eigenvector is a minus lambda I of x is equal to 0. In lambda place I am taking here 8. So we have to subtract this 8, that is minus 8 from the diagonal elements. First diagonal element is I am having 6. 6 minus 8. I get here minus 2. In the next diagonal element minus 5. In the next diagonal element minus 5. So I have to reduce this matrix into echelon form. Same procedure to find the eigenvector. So R2 minus R1 and R3 plus R1. I am making these two elements zeros by taking this R1. So here we get 0 zeros. Then I have to make this element 0 by fixing this element. So R3 tends to R3 minus R2. So finally I got the echelon form of this matrix. Here the rank of this matrix is number of non-zero rows, that is rank is equal to 2. Number of independent variables are n minus r, 3 minus 2, is equal to 1. So in here independent variable is 1. Therefore I am taking here x3 is equal to k3. From this I am writing these two equations and taking x3 is equal to k3. We get x2 is equal to minus k3, x1 is equal to 2k3. Therefore, eigenvector is equal to k3 into 2 minus 1, 1. If you take k3 is equal to 1, you will get x3 is equal to 2 minus 1, 1. Next, from these three vectors, we have to write the modal matrix. In orthogonal transformation, the first step is we have to find eigenvalues, and the next step is we have to find the eigenvectors. The next step is we have to write modal matrix. By using these three eigenvectors, I am writing modal matrix. Modal matrix is equal to first vector x1, second vector x2, third vector x3. So in orthogonal transformation, this modal matrix, it has to satisfy two conditions. The first condition is pairwise orthogonal. The second condition is its norm should be 1. When these two conditions are satisfied, then this is called an orthogonal matrix. So first we will check whether these three vectors are pairwise orthogonal or not. Pairwise orthogonal means we have to take x1, x2 and x2, x3 and x3, x1 pairwise. So orthogonality condition is x1 transpose dot x2 is equal to 0, x2 transpose dot x3 is equal to 0 and x3 transpose dot x1 is equal to 0. That is orthogonality condition. First we have to check this condition. If we take these two, so product of these two is not equal to 0, dot product is not equal to 0. Therefore x1 and x2 are not pairwise orthogonal. If you take x2 and x3, minus 1 into 2 plus 0 into minus 1 plus 2 into 1. If you take this summation, you get minus 2 plus 0 plus 2. Minus 2 plus 2 cancel. So 0 you will get. Therefore, these two are pairwise orthogonal. If you take these two, 2 into 1 plus 2 into minus 1. So 2 minus 2 cancel there. So plus 0 into 1. Therefore, you will get a total 0. Therefore, these two are pairwise orthogonal. So here x1 and x2 are not pairwise orthogonal. So we have to make these three vectors must be pairwise orthogonal. So we have to construct one vector, new vector, such that these two vectors are pairwise orthogonal. So for that the procedure is consider a into x1 plus b into x2 is orthogonal to x1. You may take x1 or x2, whatever it may be. So here I am taking x1 is orthogonal to x1. So if you substitute, that is x1, a into x1 means this vector plus b into x2 means this vector is orthogonal to x1 means this vector 1, 2, 0. So from this we will get this step a minus b plus a minus b 2a next element and next element 2b, a into 0 plus 2b, this is 2b is orthogonal to, so 1, 2, 0, 1, 2, 0. These two are orthogonal, pairwise orthogonal. Therefore, this dot product is 0. Therefore, I am taking here a minus b into 1 plus 2a into 2 plus 2b into 0 is equal to 0. From this, we get b is equal to 5a. So, if you substitute this 5a here, you will get, so a minus 5a minus 4a, 2a, so 2b 2b means 2 into 5a, 10a is orthogonal to 1, 2, 0. So put a is equal to 1 by 2. You will get, I am reducing this one by putting a is equal to 1 by 2. So you will get finally minus 2, 1, 5 is orthogonal to 1, 2, 0. Now, so I am writing here model matrix is equal to first vector 1, 2, 0 and the second vector minus 2, 1, 5. New vector, this is new vector, and the third one is 2, minus 1, 1. Check these three vectors are pairwise orthogonal or not. So if you take x1 transpose dot x2, 1 into minus 2 plus 2 into 1, minus 2 plus 2, 0 plus 0. So these two are pairwise orthogonal. So if you check this one, minus 4, minus 1, minus 5, plus 5. So this is also 0 you will get. So if you take these two already pairwise orthogonal. Therefore all the three vectors are pairwise orthogonal. So this first condition is satisfied for this model matrix. The second condition is its norm should be 1. Norm, length of a vector. This vector is 1 and should be 1, and this vector length should be 1 and this vector length should be 1. If you check, so root of 1 square plus 2 square plus 0 square. Here we are not getting the length 1. You will get root 5 here you will get, not 1. Therefore, we have to normalize this model matrix. So, normalized model matrix is, so each element you have to divide with its norm. So 1 divided by its norm is root 5. So 1 divided by root 5. 2 divided by root 5. 0 divided by root 5. Then the next. So this root of, this length is root of 4 plus 1, 5 plus 5 square and 25. That is 4 plus 1, 5 plus 25, 30, root 30. So you have to divide each element with root 30. So minus 2 divided by root 30, 1 divided by root 30, 5 divided by root 30. The next one is 2 divided by root 6, minus 1 divided by root 6, 1 divided by root 6. So if you check this norm, so it is 1 divided by root 5 whole square plus 2 divided by root 5 whole square, this whole square plus this whole square plus this whole square root. So this whole square is 1 by 5 plus this whole square is 4 by 5. So 1 by 5 plus 4 by 5, 1, root of 1, 1. So like this, each vector length is 1 here if you check. So here this condition is also satisfied. So here normalized model matrix P. In this matrix, first condition is all the vectors are pairwise orthogonal. The second condition is length of each vector is 1. These two conditions are satisfied. Therefore, this P is an orthogonal matrix. That is orthogonality condition. When we will say that this P is an orthogonal matrix, if P inverse is equal to P transpose. So after this, we have to find diagonal matrix, that is D. We need D to write canonical form. This diagonalized matrix D is equal to, we know that in diagonalization, P inverse AP. Here P inverse is nothing but P transpose. So you have to write the transpose of this P. So P transpose A, a given matrix A and P, if you write this P, if you multiply these three matrices, you will get a diagonal matrix 2, 0, 0, 0, 2, 0, 0, 0, 8. These diagonal elements are the eigenvalues of A. So we can use this diagonal matrix here to write the canonical form of the given quadratic form. So the canonical form is, formula is y transpose dy. So here y transpose y1, y2, y3, d we are writing is here this diagonal matrix, and y is y1, y2, y3. Column vector, this transpose is this one. So if you multiply these three things, you will get 2y1 square plus 2y2 square plus 8y3 square. This is the canonical form or sum of squares of the given quadratic form. So finally, how to find the canonical form of the given quadratic form by using orthogonal transformation is, the first step we have to find eigenvalues of a matrix, and the second step eigenvectors of the matrix, eigenvectors for eigenvalues. The third step is we have to write the modal matrix, and this modal matrix has to satisfy two conditions. The first one is pairwise orthogonal. Second condition is its norm, its length must be 1. If not, then we have to convert these vectors into this normalized model matrix, and after that we have to find diagonal matrix D. After finding this D, we are writing the canonical form of the given quadratic form by using y transpose dy. Finally, you will get the canonical form of the given quadratic form. Thank you all. Subscribe our channel.